Welcome, ladies and gentlemen, to some Integrated 2 Math. In today's episode, we will be discussing Chapter 9.1.2, which is writing quadratic equations in vertex form. Before we talk about the quadratics in any form, I do want to graph the most basic form of a parabola, and the reason why I'm doing that is because I want to illustrate some visual features about it. So I'm going to go and just use this xy table. I'm going to plug all of these values into x squared. And if you want to hit the pause button for a second and jump ahead of me, that's fine. See if you can get these values before I can. You will absolutely be able to do it. So I'm going to get a 0, a 1, a 4, and a 9, a 1, a 4, and a 9. And so take a second and check those numbers. I think I'm pretty good. I'm going to go ahead and graph this parabola on this coordinate plane here, 0, 0, 1, negative 1, and 1. 2 got me to 4, negative 2 also got me to 4. 3 got me up to 9, which is about right here, which means negative 3 will also get me to 9 as well. The most important aspect of a parabola that I want you to pay attention to before we get into vertex form is this idea of how the parabola is symmetrical. In other words, if I cut him down the middle, down his center, I can fold one side on top of the other. It's a pretty easy visual thing, but the most important thing to understand really is the symmetry, and that notice the identical parts right here. The center is 0, 0. We can call that the center, 0, 0. Sometimes people will call it the vertex. In fact, more often it's called the vertex, but it's really just the center. So that's 0, 0. But notice the points that are next to it. So from here, notice how one step away on the positive side, we have a 1. One step away on the negative side, we also have a 1. From the center, notice the distance. 2 steps away from the center, we have a 4. Notice the distance again. 2 steps on the other side, 2 steps to the left, we also have a 4. So the parabola is identical on the y's as it is from the left as it is on the right because of this symmetrical distance. Keep that in mind. That's going to play a very huge role when we go to graph these from vertex form. The parabola is symmetrical about its own vertex, and I'm going to say that expression again, so please keep that in mind. I'm going to go and erase the board real quick and come up with some examples. Give me a second. So the chapter reads writing quadratic equations in vertex form, but it's important to know before we get into vertex form what the other form is. We begin with y equals ax squared plus bx plus c. And this is what's known as standard form. It's known as standard form of a parabola. And this is the form that we often see our parabolas in. And here on the other side, I'm going to write down vertex form for you. Vertex form goes y equals a parentheses x minus h squared plus k. Now, each of these forms is just a representation of the same parabola. So I'll go and write this down, vertex form. Vertex form is here. There are advantages and disadvantages to both forms. I will go through all of those in this episode. Now, in the past, when we were graphing parabolas, we used to say, all right, if I gave you y equals x squared minus 3x minus 10, what you would do is you would factor it into x minus 5 and x plus 2. You'd say that your x-intercepts are at 5, 5, 0. My apologies, 5, 0, and negative 2, 0. And then your y-intercept would be 0, negative 10. And then you'd find your vertex to be halfway in between these factors. So it ends up becoming 3 over 2, comma, and then something. You'd plug that in to solve for the y. I'll do that right now. You get 9 over 4 minus 9 over 2 minus 10. So then 9 over 4 minus 18 over 4 minus 10, or 40 over 4 for a common denominator here. Negative 9, so negative 49 over 4. Okay, so from here, you would then graph it. You would just put in the points and go boom, 1, 2, 3, 4, 5 here, and you would do something like this, like that. Woo. And it would look kind of like this. Okay. The reason why this parabola worked out so well is it rested on the laurels of it being factorable. This parabola was factorable, but remember, as we've encountered in quadratics, not every single quadratic we're ever going to encounter will always be factorable. For example, this one, y equals x squared plus 6x minus 1, or actually I'll call it plus 1. This clearly can't be factored, but we're going to be asked to graph this thing anyway. Now, how do we do that? We could just plug in a bunch of random points and pray that we get some type of quadratic, or we can find a way to convert this standard form into this vertex form. And the way we do that is we witness the return of an old friend known as completing the square. We will see completing the square make its triumphant return in this episode. I'll put it in purple. That way it stands out. We will use completing the square to create vertex form. And then once we get this thing in vertex form, I'll tell you what the advantages are and what all the pieces are. So from here, in the past, when we did completing the square, we would usually set the equation equal to 0. Whoops, I gotta change colors. Change colors back. I would set the equation equal to 0 and then solve for x this way. But this time, I'm not going to do that, because I'm not solving for the x-intercept. I'm merely changing forms. So the y does not become a 0. He stays y. I'm not finding x-intercepts, and that's why I don't set y equal to 0. And I'm going to go and say x squared plus 6x plus 1. And in fact, I'm going to do this problem twice. I'll do it once the slow way, and then I'm going to do it once the fast way. Once you see it done the fast way, I will do it the fast way every single time. So completing the square, it's the same process except without a 0 here. So I'm going to go and subtract 1 from either side. Again, I'm doing this the slow way. And I'm going to get y minus 1 is equal to x squared. Actually, I'm going to leave myself some space here. Is equal to x squared plus 6x. And then just like in typical completing the square fashion, I'm going to add the box on the right side, which means I have to add the box on the right side. Numbers that go inside the box, half the middle term, remember from completing the square, 3's go inside the boxes. The easy side will simplify. If you remember from completing the square in the past, it'll simplify into x plus 3 squared. And that's going to equal y. This is going to become a 9. Negative 1 plus 9 is positive 8. And then I'm going to get the y by itself. And I get y equals x plus 3 squared minus 8. And again, without knowing what all the pieces are, it's just a different form of the exact same parabola. So again, what did I do? I converted this parabola into this one. So it's important to note these are the same graph. They're just written differently. They're written in different forms. Okay, just so that we can get a procedure down, I'm going to do this the fast way. All right, so I'm going to start off again. Y equals x squared plus 6x plus 1. Now I'm going to go ahead and compare this step here when I subtracted 1 from both sides. And I'm hoping this will make sense. After I subtract 1 to the left and I add the box, at the end of the day, I end up having to subtract the value back over to the right. So what I do for the shortcut is I just disavow all the subtraction on the left side altogether. And what I do is I say y equals x squared plus 6x. I put them in parentheses, and I put a plus 1 hanging out on the outsides. Give me a second. I have to widen up the board a little bit. Okay, so I had to widen up the board just so I could do some more work here. But okay, so again, I kicked the 1 on the outside. And again, what I'm going to do is I'm going to add the box. Now, ordinarily, when I add the box on the right, I have to add the box on the left. But I'm not going to do that, because eventually that box needs to move over to the right side, which means I'm going to have to subtract that box. So instead of adding the box to the left and then subtracting the box to the right, I will bypass that step and simply subtract the box on the right side. So I've kept the equation balanced because I've added something and then I've subtracted something. So nothing has changed because the addition of the thing and the subtraction of the thing is like adding 0, which doesn't change a thing. Okay, the numbers that go inside the boxes are 3's. We knew that from the last iteration of this problem. And now from here I get y equals x plus 3 squared. This dude becomes a 9. 1 minus 9 is negative 8. And by doing way less space-taking stuff, I've gotten the exact same thing as the blue guy down there. Okay, let me clean up the board real quick, and I will talk about each of the pieces. Now that I've gotten this thing in vertex form and cleaned up the board, let's talk about what each of the pieces does. Vertex form is advantageous because it tells you clearly what the vertex is. The vertex coordinates will always be h, k. Always. So in the case of this particular example, and if you want to know why it's h, k, you'll have to watch the next video on function transformations. You'll see it happen. But in this example here, I know what you're thinking. You already know the vertex. You think the vertex is 3, negative 8. But that would be wrong. The vertex in this case is actually negative 3, negative 8. Now again, I know exactly what you're thinking. Wait a second, you just said the vertex was h, k. This guy's positive. Well, look at the original formula. The formula always has what's happening inside the square. They have it as x minus h. This is x plus 3. So remember, I'm not subtracting anything unless I see this x plus 3 on the inside as x minus negative 3. And that's how this form can be adjusted to look like this form. Remember, I always have to be subtracting the inside to get my x coordinate of the vertex. So remember, when you see this plus 3, it really means you're subtracting a negative 3 from the inside. Just keep that in mind. Okay, so once I have the vertex, what I'm going to do is I'm going to put it into a table. I'm going to put it into a table. And actually, I'm going to move my table a little bit over. Move my table over here. And what I do is I always put my vertex in the center of the graph. And what I'm going to do here is I'm going to pick a number that's really, really easy to plug in. Well, that number is going to be 0. Now, what happens when I plug a 0 into this equation? Well, remember, before I plug it into my vertex form, I actually had a standard form of this thing. My standard form was x squared plus 6x plus 1. And I told you that there were advantages to the other form. Well, the advantage to this form is that plugging in 0, the easy number that we chose, is much easier here than it is here. But we will use him in a little bit. So if I plug 0 into here, I get 1, piece of cake. Now remember, at the very beginning of this lesson, I talked about symmetry. In other words, the parabola was identical on the right side of its vertex as it was on the left side of its vertex. Using this knowledge, that means that the 1 that appears down here will also appear here. Remember, we've got a 1 on the right side of the vertex, right? This is the vertex. We have a 1 on the right side of the vertex, which means we have to have a 1 on the left side of the vertex. The question is, what x-coordinate makes that happen? Well, remember the distance, right? How do I move from negative 3 to 0? I had to add 3 to him to become 0. So how do I get back to the corresponding space on the left side? Well, remember the distance, right? If I'm going to add 3 to get to here, then I have to subtract 3 to get to here, making this negative 6. So I hope that makes sense. Let me go and get a coordinate plane on here, and we will graph this thing. Give me a second. And now that we have our coordinate plane, I will go and go to my vertex, which is negative 3, negative 8. So negative 3, negative 8 is here. And I'll go and label him negative 3, negative 8. And I'll go and put in my points. 0, 1 here. Negative 6, 1. Whoops, that's 0, negative 1. Sorry. 0, 1 is here. Negative 6, 1 is here. Notice the symmetric nature of the parabola. Notice, and that was supposed to happen, right? Because the parabolas are all symmetrical. So here we go. There's the symmetry, and there's our graph. So hopefully the completing the square makes sense to you. I will be back in another video with some examples of this, and I will see you in the next episode.